Hey guys, how's it going? So today we're going to be covering MobileVIT and we're going to be coding it up from scratch. Before we start with the coding component, I thought it would be a good idea to kind of like walk you through the three papers so that you can appreciate some of the improvement that they did from VIT1. So essentially, the main idea behind MobileVIT is to integrate the CNN with Vision Transformer. So the author asked themselves if it would be possible to leverage the strength of these two components in order to build a very lightweight and low latency network that can be used for infrared or edge devices. So I thought it was a pretty impressive ideas that they came up with and how they integrated these two blocks. So I'll be covering these method in more details. So without wasting any time, let's get into it. So when we build computer vision models, we always want a very lightweight model, especially if we're building for mobile or edge devices. And CNN have quite been dominating that component there. This is mainly because of their special inductive bias. Not only that, but special inductive bias being one of the reasons. And you can think of this special inductive bias as the assumptions or prior knowledge built into the architecture of the network. So we can look at things such as locality, pooling, weight sharing. So locality is whereby each neuron is connected to a small input. So we learn edges. Then weight sharing is whereby we have the same weight used for each connection, right? So essentially this enables the model not to learn anything from scratch due to that prior knowledge. Not only that, the author do also admit that it enabled them to learn representation with fewer parameters across different vision tasks, right? However, because of their spatial, spatial local, we want to learn global representation, and which is what VIT are good for, right? However, VIT are data hungry, so increasing the parameters improve the performance. But we know that when we increase the parameters, we're not making a very lightweight model. So it comes at the cost. So with that, they also asked themselves if would it be possible to combine the strength of CNN and VIT to build a very lightweight, low latency network for mobile vision tasks. So what they did was to introduce VIT, a lightweight general purpose vision transformer model for devices. So the author observed previous research and they've realized that these hybrid models, by these hybrid models I mean like the models that try to integrate CNN and VIT, are still heavyweight and are sensitive to data augmentation. Because VIT are data hungry, like I said, so they require extensive data augmentation for them to actually have accurate or acceptable performance. So, but these lead to these models to have more parameters. They also state this to support this. They state that they've realized that removing on that style, removing the data augmentation caused the model to drop in terms of accuracy from 78 to 72%. So yeah, I think some of these components are quite important to support VIT to actually achieve adequate result. So they state that it remained an open question to combine the strength of CNN and transformer to build VIT models for mobile vision tasks. Mobile vision tasks require a lightweight, low latency, and accurate model to satisfy device resource constraint. So some of these previous papers, what they tried to do was to optimize only for floating point operations. However, ignoring important factors such as memory access, degree of parallelization, and platform characteristics can lead to a model that does not perform well in terms of latency. So what they tried to do was not to look into the floating point operation, but also to look into the lightweight, objective, general purpose, and low latency. So they did this by actually combining the benefits of CNN, which comes with the special inductive bias and is less sensitive to data augmentation. Whereas with VIT, it has the input adaptive weighting. So by this, because of we take an image, we break it down into patches. So some of these patches are going to be weighted more than other patches. This is mainly because of the attention mechanism. And VIT models tend to have this global processing power, so they can learn global information, whereas CNN can learn local information. So that's like the most important thing between these two models. Before we get into the mobile VIT architecture, let's look into the standard VIT model, right? So we can think of this as like VIT essentially reshape the input. So let's say we have an input image denoted as this, like we have height, width, and channel. So we reshape this image into a sequence of flattened patches, right? So this end here refers to the number of patches, and PC refers to the number of pixels in the patch with height and width. Then these patches are projected into fixed dimensional space, and then we learn the interpatch representation using transformer blocks. So we can have a stack of these blocks. The computation cost of this self-attention inversion transformer is quadratic. So we have always knew that. So I think what we're gonna do is that I'm just gonna try to kind of like visualize my explanation. So you can think of like this image here, right? It's getting split into these patches. So we flatten the image into patches, right? Then we have a linear projection of flattened patches. So we create a lower dimension of linear embedding. Then we add, we include positional embedding. So we try to say the reason we include positional embedding is because we want these images to have a position. So we know that, okay, this is at the top left corner, this is probably at the top right corner. So there's definitely a pattern in this image. So then say we needed to include a position in this case. Then what we do is that we feed these patches into the transformer encoder, and we have a multi-layer perceptron head, and yeah, we have a classification. But this is more or less a standard version transformer architecture, and that's what it does. So yeah, I think let's continue and look into the architecture. Looking into the mobile architecture, so what I've done was to actually paste this image here so that I can explain it from a visual perspective. So let me just zoom in here. I'm just gonna do so. So essentially, we can think of like we have an input, right? We have an image represented with like height, it has width, and it has channel, right? So for this given image, what we do is that we try to apply a standard convolution. So n by n convolution. So this could be 3 by 3 convolution. Then we pass this output of this into a pointwise convolution, 1 by 1 convolution. So the intuition behind this convolution is that the n by n convolution, essentially we encode local information. That's why here they wrote local representation, right? We encode local spatial information, whereas this pointwise convolution, we project the tensor into a higher dimension. So you see here we're moving from channel to this D here. So this D here essentially is greater than C. So here we expand the channel into higher dimensional space. So this is enable us to learn linear combination of the input channel. Okay, so the author stated that while it is effective to learn local representation, however, we're gonna need a method to learn long range non-local dependencies. By that I mean like a model that can learn global representation. So what they did was to try to assess, actually let's go to the specific text. They found that actually self-attention was actually one of the candidates for learning that non-local long-term dependency objective. So this is mainly because vision transformers with multi-head self-attention have shown to be effective for visual recognition tasks. So how did they then integrate this vision transformer into the mobile VAT architecture? So what they did was to unfold that output of from the position-wise convolution. They unfolded it n non-overlapping flattened patches, denoted as this. So we can think of this as P denoting the number of patches. So this output here is then fed into the transformer to learn the interpatch relationships. So from a visual perspective, let me show you how this looks like. So we can think of like the output. We know that the pointwise convolution essentially produced this. Then we project this into this. Then we apply the transformer model. Right. So I hope that makes sense. So they state that unlike VAT that loses the spatial order of pixels, mobile VAT neither loses the patch order nor the spatial order of pixel within each patch. Therefore, we can fold this to this, right, whereby XF is projected to lower dimensional space using the pointwise convolution. So we kind of like reversing back, we're going back to the original dimensions. So we're using this position-wise 1x1 convolution. So yeah, that's what this means. Then they say that we combine it with X. So we take the input, we concatenate it with this output here. So from a visual perspective, we can think of like this output here. We take this, then we use the pointwise to get this output. Then we concatenate the input with this output here. Then after that, we apply an n-by-n convolution. So this is stated here. Another n-by-n convolution is used to fuse these concatenated features. Note that because XUP encodes local information from n-by-n region using convolutional convolutions, which encoded global information. So the point is that we have both local and global informations, right? So yeah, that's what it states here. So I think overall that's how it works. Now let's go into more other components. Relationship to convolution. So the author state that their model is actually similar to convolution. So a standard convolution can be viewed as a stack of three sequential operation, right? The first being unfolding, then we have the matrix multiplication, then we have folding. So VAT essentially tried to replace this matrix multiplication with a global processing component. So we know that that's a stack of transformer layers, right? So here it was the local processing, so hence the matrix multiplication. So this makes the mobile VAT to be viewed as a transformer as convolutions. So it still follows the similar operations of convolution. The second component is lightweight. How did they then achieve the lightweight objective? So we're looking at the previous papers. One thing that we realize is that some of these VAT models are quite heavy in terms of their weight. So the author believed that the issue lies primarily in the learning global representation with transformer. So for instance, they state that for a given patch, previous work convert the spatial information into latent by learning a linear combination of pixels, right? The global information is therefore encoded by learning interpatch information using transformers. So as a result, these models lose image-specific inductive bias. Because of because of they lose this inductive bias, which is inherent in CNN, then they end up learning more information. So they have to be trained for more compared to CNN. So I think that's how I'm interpreting it, is that with CNN, if like you have like CNN properties, then because of you kind of like keep that inductive bias, then you wouldn't actually be able to train more, and the model wouldn't be as data hungry. So essentially what I'm saying is that you can actually be able to build a very shallow narrow network, whereas with models that loses inductive bias, you end up building these deep models that have now massive parameters inside them. So I think that's what the author were trying to say here. Anyway, I'm just gonna scroll down. So in terms of computation, they state that the computation cost of multi-head self-attention in VIT is quite bigger than the VIT. So in theory, we can think that MobileVIT is actually inefficient because of the big O notation. But when we test them in practice, we realize that MobileVIT is more efficient than VIT. So yeah, I think some of these models hide behind these big O notations, but when you start implementing them, you start to realize that actually they are not efficient. So it's a similar thing that the author says here, is that MobileVIT has a 2x fewer floating point operation and deliver 1.8 better accuracy than the dead-on model. So yeah, that's because of MobileVIT is quite narrow and shallow compared to this model. So I think it can all comes down to the number of parameters, how heavy the model is. So I think this big O notation at some point can be deceiving. So in terms of the mobile architecture, I'm just gonna look here. So they use a standard 3x3 standard convolution. This is followed by the MobileNet 2. So we can think of like the mobile VIT as a block, then it's getting stacked with components such as MobileNet VI2. Then they're using the switch activation functions. The spatial dimension of feature maps are usually multiples of 2. The MV2 block in MobileVIT network are mainly responsible for downsampling, and therefore these blocks are shallow and narrow in MobileVIT network. So the switch activation function can be represented as x by sigmoid. Then you put x here. So also you can have a beta here as a trainable parameter. Okay, so but the point is that unlike ReLU, switch is smooth and Boolean function that can take negative values. So this essentially can help reduce the dead neuron problem, where a neuron is actively turned off due to a negative input. So this activation function has been shown to be quite robust to adversary attacks and other functions compared to ReLU. So that's why I think maybe based on the experimentations that the authors did, that's why they decided to use it in this case. Anyway, so the next component is the multi-scale sampler for training efficiency. So the idea behind multi-scale sampling is to randomly select different scale of input image, alright, during training, so that the network can learn to recognize object at the different scale and location. So these techniques involve selecting a scale factor and resizing the input image accordingly. So during each training iteration, what we do is that the network is presented with a batch of images that have been resized to different scale, and the network is trained to recognize object at different scale. So the advantage of doing this is that the model can actually learn to the network learn features that are invariant to scale and improve the ability to generalize to nuance in data. Okay, now looking into the second paper called Separable Self-Attention for Mobile Vision Transformer. So the main improvement that the author is trying to make from the first mobile VAT was to try to handle the multi-self-attention time complexity. So we all know that if we have a number of tokens or patches in this case, and we can denote this as K, so these tokens have to attend to one another. So we end up having the time complexity of K squared. So the time complexity is quadratic. So this did actually have an impact on mobile VIT. So it slowed it down. It was quite slow, right? Moreover, the author tried to reduce some of the expensive operations that are used within like the multi-head self-attention. This includes things such as batch-wise matrix multiplication for computing the self-attention. So what they do is that they introduce what we call separable self-attention method with the linear complexity. So we're going to discuss that component in more detail. Not only that, but they also introduce element-wise operation for computing the self-attention. This is to replace costly operations such as batch-wise matrix multiplication. So pretty much their implementation, they saw a 3x improvement. So I think 3x is quite mind-blowing. Just shows like having these linear attention techniques can actually improve the overall implementation, the latency of these models. So we're going to jump into it and try to understand how they did it. So there's been quite a lot of attempt from previous authors who try to actually linearize the self-attention, right? So if we take a look at something example like linformer, the author tried to decompose this self-attention operation into multiple smaller self-attention operation. This was through the linear projection, and this reduced the time complexity of the self-attention from quadratic to linear time, right? However, the author do realize that even if that's the case, but these models, they still use costly operations. This is batch multiplications. So they are not necessarily designed for resource constrained devices, such as mobile device. So that was one way why they didn't use some of these models that have been developed in the past for linearizing the self-attention. Not only that, I think I'd like to add that these models, like the linear self-attention models, the problem is that some of them have been developed mainly for specific use cases, and they can't necessarily be used for different use cases. So you're gonna see a performance drop there. So yeah, they also suffer from performance. Hence, like we see from modern research, why these linear models, they're not heavily used. People, they still use the quadratic self-attention because they try to maximize performance as possible, right? So that's another thing. But yeah, the author, what they do is that they're saying that, okay, we're gonna come up with a separable self-attention, but we're gonna make sure that we use summations and multiplications instead of using these expensive operations such as batch-wise matrix multiplication. So I want to jump into here a little bit about what they mean by batch-wise matrix multiplication and summation, just to kind of like give you guys a perspective. So we can think that each value in a sequence, right, is multiplying by corresponding weight, right? So let's make example here. Just consider this as a pure example. So let's say we have the sequence, and the sequence of 2, 4, 6, 8 here. Probably with the query, our query is probably 4, right? So we need to compute the weighted sum of the values in the sequence. So we need to compute weighted sum of values in sequence, right? So I just want to kind of like show you the difference between these batchwise multiplication and summation, element-wise summation. So in VIT, like in Vision Transformer, let's say you have some sort of like a weight, right? Maybe this weight is size n by n, right? So where you can say where n is equals to the sequence length. Okay, so you can say sequence length here. Okay, so just to visualize it, so we can say we have n by n. I think here we have a row, so like so. So essentially each row is a vector of how similar each value is to the query. So this here is how similar it is to the query, how similar it is to the query. Okay, then we can have value here with d. So d is denoting the dimension of the value. So the weighted matrix will be multiplied with the matrix value, right? So you can see that you have these matrix multiplication between keys and weights. So that's that. But now in MobileVIT, what they mean by element, element-wise multiplication, is that instead of thinking about matrices, now you can think about vectors. So we have a weight vector, right? So of size n. Okay, so where the first, we can denote this as like wi, represent the similarity. Yes, wi represent the similarity with the ith. So the value ith here, how similar the weight is. So it's like a value to value similarity in a sequence. So how you get it, you say maybe wi equals to q times vi. So this is like the query. Then you multiply by the ith value, in the sequence, and you're gonna get the weight. But you can see that here we set up the queries for. Then we said that this is the element in the value, so which is also an element. So this is an element operation. So there is no necessary a matrix multiplication. So that's what they do. So essentially, in a nutshell, the key takeaway is that doing it this way is much more efficient than using matrices and weights within those matrices. Could be quite expensive. Yeah. So adding into some of the techniques that the author used, such as using element-wise operations to improve the performance, they also used mixed precision training, using different FP, this could be 16 or 32, to improve, I think, on the training throughput. Then they used efficient optimizers and knowledge distillation techniques to compress the model. So I've been saying that they trying to introduce this separable self-attention with linear complexity, but what is the main idea behind this technique, right? So they state here that, okay, the idea is essentially to compute the context score with respect to the latent token, right? And these tokens are then used to reweight the input token and produce the context vector, right, which encode the global information, right? Because the self-attention is computed with respect to latent token, the proposed method can reduce the time complexity of self-attention in a transformer by a factor of k. Okay, so what does this mean essentially? So let's take an example. So let's say we have input, right? We have inputs. So right, and let's say obviously because of here it's MobileVIT, our input is going to be patches, right? So we split the image. I'm just taking you through step by step so that you understand what does this mean essentially, right? So that's why I'm explaining it from scratch. So let's think of like we have an input. We split this input into non-overlapping patches, right? So that's what we do. It's like they can call this tokens at some point, but yeah, it's just patches. So these are flattened and projected into higher dimension, right? Flatten these and we project them. Okay. Then we have the second component, which they mentioned, which was a latent token, right? So we're gonna denote this as L, and this is a learnable parameter, right? It's gonna be a learnable embedding vector added to the input sequence, right? So what we do is that we're gonna perform a dot product. This is step 3. So we're gonna perform a dot product between the latent token and each patch. So we take this thing that we denoted here. So we're gonna denote patch as P. So we're gonna take L, our latent token. We're gonna do a dot product, right, with each patch, right? So this essentially is to get the similarity between the patch and the token, L token. So we get the similarity between the two, to get the similarity between the two components. Then we pass these through a softmax to get a context score. Okay, now we have those context score. You understand how we get them. We have this latent, we have these patches, we multiply them with this latent token, and we get the context score. We get the scores, but we still need a softmax, so we push them through a softmax to get the probabilities of these, right? Then yes, I said probabilities. Then this is going to tell us the importance of each, the importance of each patch. Right? It's going to tell us the importance of each patch. So now we have the context score, but the problem is how do we then get the context vectors, right? So that's the next step. So with the context vectors, we take the input embedding, right? We take the input embeddings, then we reweight them. Yes, we reweight them by the context. Yes, by what we got here, by this context vector. So we reweight them by the context score, right? And this gives us the context vectors. So you get it. So that's how essentially it works. And some of you might be, yes, why are they saying now this is linear? This is linear because you only have to attend to this latent token, and that's it. So each patch only has to attend to this latent token. So remember that. Okay, let me do this. I want you to understand this. Remember that with attention. So with attention, yes, each token has to go to all the tokens, right? You need to go here, you need to go here, you need to go here. No, just like that. So this is quadratic because you need to go to each token. So, but now, with this method that they're proposing, it's like you have each token, it gets reweighted based on only this latent thing here, right? So it becomes a linear thing. That's what it means, right? So I hope it made sense. I hope it makes sense for you to get a deeper understanding. I'll definitely recommend checking the illustrated transformer by Mr. Alama. He explained self-attention in a very good way. So you will understand that, okay, how these how we get a score. For instance, let's say we have a word here. We have like thinking attention, like, something like this. We have something like thinking attention. So what we do have query, we do have value, we do have keys, and one of the things that we do as process here, I think here we also have initialized wait for query, we have keys and stuff like that. But one of the things that we do, right, is that there's a part whereby we have to take the query, like, and we multiply it by the key, right? And this is key 1. Then we take the query 1 and multiply it by the key 2, right? So this key 2 is coming from this second weight. You can think of these as weights. So you can see that we're still on phase 1, by the way. We're still on the weight 1. So we have to do this like for every weight. So it's gonna be Q1 multiplied by Q3 if we had another weight here, right? And we need to then apply softmax to these. So we get a score, then we apply softmax, right? So to these scores that we get here, because this is a dot product between key and key, query and keys. But essentially, that's something along those lines. But here, you can see the good thing here is that we don't have to go through all the queries. We don't have to do that. Each patch just goes to the latent. So we don't go through each query. I hope that kind of like gives you a broader, maybe a better perspective about what does this explanation mean here, right? Yeah, I hope it helps. But anyway, let's continue. They say that a simple yet effective characteristics proposes that it uses element-wise operation, summation, multiplication for its implementation. So replacing the quadratic multi-head attention with a linear one. Okay. Now looking into. Let me just scroll down. Sorry about that. Looking into this, pretty much this is what I was actually explaining here. So pretty much exactly what I explained. So I'll come back to this diagram here. Sorry about this. Just gonna try to get to the right. Okay. So for us to appreciate their method, let's try to understand multi-head self-attention first. So the multi-head self-attention essentially takes in an input comprising of k-dimensional tokens, or we can think of this as patches, embeddings. This input is then fed into 3 branches, namely query, key, and value. So each branch is comprised of a number of heads, right, like linear layers, which enable the transformer to learn multiple views of the input. The dot product between the output of linear layers and query and k is computed simultaneously for all heads, and is followed by a softmax operation to produce an attention. You can think of this as a context mapping. Another dot product is then computed between I think the output and the output of a linear layer in V. So this is a V vector to produce the weighted sum output, right? So the output of heads are concatenated to produce the tensor with k-dimensional tokens. Okay, so essentially from a visual perspective, firstly, thanks to J. Alama for this beautiful visualization. But essentially we can think of it as like we have input sequence, and what we do is that we firstly embed this. Then in the original attention paper, they had 8 heads. So we're gonna split this into 8 heads. Then we multiply x by these weight matrices. Here we have query, key, and value. Then after that, we apply the self-attention for each head. Then we're gonna have the output. Then we concatenate all of these output to get a single output here, like so. So yeah, that's that. So the main intuition bits behind multi-head is just so that like we can have a multiple views of the input. So if we had like only one self-attention, then some of the weight could have dominated. Some of the weight that we're currently attending to would have dominated. So to avoid those kind of things, that's why we have multi-head self-attention. And we get like I said, we get a different perspective of these weights in the process. So anyway, now let's look at how then the separable self-attention multi-head attention is different, or it's similar to the original transformer implementation. So the authors state that they were definitely inspired by the multi-head attention. So the input is processed using the 3 branches also in this case. So input I, you can see here they say I instead of query. That's the first thing to notice. Then they say K with another K, then they have a value. Then they say the input branch I maps each dimensional token in X to a scalar using a linear layer with weights. So let's try to break this one down. So we can see that they say that essentially this I, which in this case I think this is going to be a latent token, right? It's going to take X, which we can think of X as tokens or patches, to a scalar. So we can think of this as token is being mapped to a scalar. So a dot product between this is going to get you a scalar. Okay, because we have multiple tokens, we have multiple patches, then we get multiple scalars. So what does this thing mean? It means that we get a D, they're calling it K in this case, K dimensional vector. Okay, K dimensional vector. So anyway, let's continue. They say that the weight serves as the latent node. Yes, so this linear projection is an inner dot product operation and compute the distance between latent and X. So like we said, yes, we take this I, which I knew it was the latent token, then we multiply it with the patch, then yeah, that's that. Then we get K dimensional vector because each token has to be multiplied with this latent token here. So we're gonna get a vector like so. I'm writing it as if it's a matrix, but yeah, it's more like a vector, like so. Anyway, then they say a softmax operation is then applied to this K dimensional vector to produce the context score. Yes, so after we got in this vector, then what we do is that we apply the softmax operation to get the scores. So they state that unlike transformers that compute the attention score of each token with respect to all the tokens, yes, so with transformer it's quite heavy there. So we compute the context score with respect to the latent token, which is pretty much what I explained. If you guys can remember, is that now we only take the number of tokens like in shown in this, and we multiply by this, we have a dot product with this latent token, unlike with the transformer whereby each weight has to attend to other weights. So it's the same thing that we spoke about. So they state that this reduces the cost of computing attention score from quadratic to linear. Yes, that's true. Then they state that the context score are computed, are used to compute the context vector. Okay, yes, they're used to compute the context vector. Specifically, the input X is linearly projected to a d-dimensional space using key branch with weight. Yes, so remember that we said that we have what did we say? We said that we have I, right? We have key and we have v. So this one we knew that it was for what we just explained now, latent vectors, and we get the score at the end of the day. That's what we care about. We get the score. So we apply things like softmax and all of those things. We explain this, right? We know what's going on. But now you see what they say. They're saying that X is linearly projected to d-dimensional space using the key branch. So which means that this key branch is going to take the input and it's going to project it to d dimension. Okay, so it's going to take the input, all the patches. So the main goal is to project this into d dimension. Then to produce an output, the context vector is then computed as a weighted sum. So you see here that the project dimension of the input is then multiplied with this score that we got there. So then after we do that, then we get what we call context vector. That's how we got a context vector. Okay, so hope that makes sense. Then they say that the context vector, which is CV, okay, yes, analog to attention matrix, in a sense that it encodes the information from all tokens in the input X. Yes, it makes sense, because if we look at the diagram here, it encodes, because let me just scroll down here. I want you to pretty much understand, like I said, that the key projected this to d dimension. As you can see that because now we have these context score, this is going to get multiplied with this is going to get multiplied with this is going to, so you see here we have this dot product that is going to happen, and this is going to give us the context vector, what we have been looking for, this guy here. You see, so these have different objectives. So let me just go back, just gonna try to zoom out. So yeah, that's that. Then they state that the contextual information encoded in CV is shared with all the token in X. To do so, the input X is linearly projected to d-dimensional space using value branch with weights, so followed by ReLU activation to produce this. So the context information in CV is projected with via. Okay, so yeah, I think here they say that V is also gonna get multiplied with the context vector. So the resultant output is fed to the output linear layer. So yeah, I think it's just to show you from a visual point of view. So you can see that here V, we apply a ReLU, then we get D by K by D, then we have another, we broadcast element-wise multiplication with context vector, then we apply another linear, then we get the output like so. So yeah, I think that's that. But yeah, it's kind of like walk you through the intuition again. I'm gonna repeat this. So the context vector is analog to the attention matrix in the sense that it encodes the information from all tokens in the input, but it's cheap to compute, right? The conceptual information encoded in CV is shared with all the token in X. Okay, to do so, the input X. So yeah, to share the conceptual information across all the tokens, right? So to do so, then you need this V, right? That's the intuition. You need this V. So the input X is linearly projected to d-dimensional space using V. Yes, you see. So you have this contextual vector, but you need these tokens, right? So that's how I think that's why we needed to project this. We applied ReLU and stuff like that to that. So I think that's all, to be honest. The next thing that they talk about here is just like pure experimentations, which we're gonna get into. So I feel like what I will do is that I'm gonna code up the MobileVIT one first. Then in the next video, I'm gonna code up MobileVIT 2, right? Just to avoid making this video long. Yeah. I hope you guys enjoyed this. But yeah, let me know if you want me to improve something. I don't mind doing that. But anyway, let's get into the code and try to code up this method. Okay, now we will be actually coding this MobileVIT. Before we get into the code, I just want to say that I'll actually be following this architecture here so that you actually know where we are currently at. So as you can see that the first block here is a convolutional layer of 3 by 3. Then we have strides which is equals to 2. So that's the first block that we're going to build. Yes, and the first thing that we're gonna do is to import the libraries. Actually, before we continue, I just wanna say that this is MobileVIT 1. So what I'll do is that in the next video, we're gonna implement MobileNet Vision 2 with PyTorch. I promise you, I'll definitely make sure that I push it. It could be tomorrow. I'll actually be able to upload it. I know that some of you might be curious about how that linear self-attention is implemented, right? So yeah, but yeah, that I'll definitely do that. I'm the man who keeps his own words. Anyway, we say that import TensorFlow as TF. Then we're gonna say from keras. I know a lot of people maybe they like PyTorch. So yeah, in the next video, the second paper, we're gonna build it with PyTorch. So we're gonna say from keras application import image net utils. Then we're gonna say from TensorFlow dot keras. We're gonna say import layers. Okay, I made a mistake here. Just bear with me with these small blocks. Then we're gonna say from TensorFlow import keras like so. Then we're gonna say import the data set from TensorFlow data set as tfds. Then the next thing we're gonna do is we're gonna have tfds dot disable progress bar. Okay, yeah, like so. So these are all the components you're gonna need. I just wanna say that I don't know if you guys are a fan of me actually coding things up from scratch. I've heard a lot of people saying that they prefer me coding things and just explaining them. Some of you maybe might not like this. Maybe you might want me to walk you through the code. So just leave a comment and let me know if this is your preferred method of me actually explaining the code. So what we're gonna do is that, like I said, we're gonna start with that block, the first one, which is the conv block. Then we're gonna take an x. We're gonna have filters, which is equals to 16. We're gonna have kernel, which size, which is 3. We saw this. Then we saw that the stride was equals to 2. Then we're gonna say conv layers equals to layers, right, dot conv 2d. Is this the correct spelling? Conv 2d. Then what we're gonna do is that we're gonna give it the filters. Then we have the kernel size. Then we have the strides equals to strides. So we have the activations, which is in this case they're using tf.nn.switch. So essentially the switch activation function is whereby we take an input, we add with the we take the sigmoid and we pass in the input. I explained this activation functions and why they are preferred in most cases than ReLU. That is because they have this smooth curve. So your ReLU set everything that is negative to 0, whereas that can cause like dead neurons or information loss. So using this smooth curve of these activation functions can actually help. I explain all of these and I code them up in my MobileVIT video, so you can check them out if you want to know more detail about hot switch, hot sigmoid, all of these efficient activation functions that are being used for these resource constrained model. Okay, the next step will be we're gonna implement. Let's go to the. Let's remind ourselves. So we can see that we have MobileVIT Vision 2. Like I said, I explained MobileVIT in my MobileVIT Vision. I explained 1, 2, 3. So check it out if you wanna know about MobileVIT. And yeah. But anyway, here the author in MobileVIT, they introduced this inverted residual block, which is what we're gonna try to implement now. Okay, so we say def inverted residual block, check x expanded channels, expanded channels. Then we have output, so I'm gonna make it a one-way output channels. Then we have strides equals to 1. Okay, then we're gonna say m equals to layers dot conv to d. So just to kind of like give you a high overview as I'm writing this code down, is that essentially we can think of like inverted residual block as like we have an input with a very small dimension. Then what we do is that we expand this this input to a higher dimension. Then we apply ReLU to make the model, to make the model more complex. Then after we have applied the depthwise and the pointwise, then we squeeze back the channel back to a small dimension. So the intuition behind this, when I read the paper, was that they had this thing called manifest of interest, is that essentially important information take maybe 1%, right, of the channel. So how do we then kind of like take the important information from like 128 of channel? So we need only important things. So they realize that if we only take, let's say, 3 channels, right, then we apply ReLU, we lose information, and the model has a very, very bad accuracy. So hence they needed to expand the model. So they expanded from that lower dimension into higher dimension. So yeah, that's why you hear terms like expanded channels, so to speak. Okay, I hope that makes sense. Then we have padding, which is equals to same. Then we're gonna have use bias, which is gonna be equals to false. Then we take in x. So yeah, this pop-up here, it's gonna make our life difficult, but anyway, let's continue. Then we have m equals to layers dot batch normalization, right? Then we have this m. So as you can see that expanded channel, we expand it, then we apply the batch normalization, right? Then because now the layers, we've expanded this input into higher dimension, we can actually be able now to apply an activation function. So an activation function add nonlinearity, so it add complexity into these models. Okay, so yeah, then we have if strides equals to 2, so we want to reduce the dimensions. So if stride equals to 2, what we want to do is that we want to say m equals to layers dot 0 padding 2d. Okay, then we're gonna say padding equals to image net utils. I wish there was a autocomplete. Correct dot correct. What's this? I think it's correct paired. Yeah, correct paired. Then we take m by 3. Then we pass in m here. So this layer can add rows and column of zeros at the top, bottom, left, and right side of the image tensor. Okay, so yeah, that's what padding does, right? So let's say you have an input image, you pad it. Yeah, so anyway, we have m equals to layers, then we apply the depthwise dot depth wise convolution. So depthwise convolution, you can think of it as we have k by k kernel by 1. So essentially the goal here is to go through the spatial dimension. So remember that we have separable depthwise. So what we do is that we divide them into 2, whereby we have a pointwise and the depthwise. So the pointwise is the one that is 1 by m denoting the number of channels. So it's gonna focus on the channel, the dimension, right? Like the channel dimension. Then with this, because it's depthwise, we have k by 1, we focus more on the spatial. Okay, so we have here 3, then we have strides equals to strides, then we have padding equals to same. So if strides equals to 1, else we have valid, like so. Okay, so essentially what this code means is that I'm gonna spread it in broad terms, is that essentially when we apply, let's say stride equals to 2, right? So when we go to apply skip connection, the dimension of the input and output are not going to be the same. Okay, so we want to make sure that the input and the output have the same dimension. So if we reduce the dimension by a stride of 2, because it compressed the channel, so we need to compensate for that, right? So yeah, that's what this code means. So sometimes when we use stride of 1, the dimension don't get lost. So that's why here I think it says if stride equals to 1, then we have padding, which is same, right? So that's what it is. We're gonna get the same output dimension and input dimension are gonna be the same. That's what it means essentially. We have that. Then we're gonna say m. Yes, after the depthwise, I think actually let me make a space here so that you understand. So you can see that we expanded this, right? Like I said, then I said that we applied it depthwise. Then after this, we apply the layer norm. So we haven't, like I said, the depthwise does not focus on this channel. So that's why here we're still gonna apply the activation function. So it's gonna be layers dot batch normalization. I think normalization. Then it's gonna be that. Say I heard that USA use Z. In UK, I think they use S. So I'm surprised this is S. So it's gonna be M equals to TF dot NN dot switch. Yes, we apply the activation function because we're still on the higher dimension, so we haven't reduced the channel that much. So we're gonna say M equals to layers dot conv 2D. Then what we're gonna do actually, we go into, it's gonna be conv, I think it's gonna take the output channel. What did we call it? Output channels. Yeah, output channels. Then we have one padding. So you can see here that I'm going down. Can you see this? I'm squeezing it. I'm going down to lower dimension. Can you see this? So I expanded, when I started, I expanded the channels. That was, I increased the channels, but now I'm going down by applying this pointwise convolution. So this is going to be same padding. Then we're going to say use bias equals to false. Then we're going to take M like so. Then here we have M equals to layers dot batch normalization. I think it would be better if I copy this, because I keep on typing and there's a, but can you see we don't apply we don't apply activation function this time. Why? Because of we have reduced the number of dimensions, which makes sense because like I said that when we have the smaller dimension, that's what the paper MobileNet they've realized is that when you have a lower dimension, when you apply an activation function, then you're going to have information loss. So when you don't apply activation, that's why they call it inverted residual block. Then I think they said linear something. I forgot their full name, but they have like linear something. And the reason there is a linear in that name, it is because of the final thing here does not have a non-linearity activation function. Okay, I hope that makes sense. If it doesn't, just like I said, just you can check up my other video about MobileNet, just to get a better perspective. Yeah, I'll link a paper so that you guys can actually check it out. Then we're gonna say tfmats dot equal x dot shape. Then we're gonna have output channel. Then we're gonna say end strides equals to 1. Then we return. So like I said, that the dimensions of the input and output have to be the same, and for us to know that they will be the same, if stride equals to 1, because if we stride equals to 2, we reduce the dimensions, you see. So that's why when stride equals to 1, then we can add the input and the output. Okay, so here we can say I think I have to do this. Then I can say take the output, which is M, take the input, which is X. However, if this is not the case, you can return M. You don't have to add the skip connection thing. Okay, so yeah, I think that's all. Let's move to another block. Implementing the multi-perceptron. So we're gonna say df multi-perceptron. We're gonna take X, Then we're gonna take hidden units. Then we're gonna say drop out rate. We're gonna say for units in hidden units, we're gonna say x equals to layers dot dense. Then we pass in the units here, and the activation function is gonna be equals to tf.nn.swish. Okay, we pass it x, so then we say x equals to we're gonna regularize this by applying drop out, then we're gonna say drop out rate. Then we're gonna pass in x here, drop out rate. Okay, that's fine. Then when we're done, we're gonna return x. Okay, so looking at the at the architecture again, so we need to build this transformer block. So that's what we're gonna build now. Let me just create a space like so. We're gonna say def transformer block like so. Then we're gonna take x transformer layers, then we take in the projection dimension, so we're gonna call this projection dim. Then we're gonna say num of heads is gonna be equals to 2. Okay, then we say for I in range of transformer layers, right, what we want to do is that we want to first normalize the layer. So we're going to say xi equals to layers equals to layer normalization we apply the epsilon. So this is just a small number to make sure that we don't divide by 0. Epsilon. Okay, there is it here. Autocomplete. Thank you. So it's gonna be like so. So essentially we subtract the mean from the input and we divide by standard deviation, and we have our parameters for this layer normalization, and we use this epsilon to make sure that we do not divide by 0. Okay, that's that. Then we need to now apply the attention or the multi-head attention output equals to layers dot multi-head attention. So we take nums of head equals to num head. Then we have key dimension equals to projection dimension, which is gonna have the dropout rate. We're gonna call this dropout equals to 0.1. Okay. It's complaining here. Did I call this num of heads? Yes, so it's missing an S. Like so. Oops. Yeah. Then this is gonna take in x1 and x1. Then we apply the skip connection, which is x2 equals to layers. Then it's gonna be dot add we want to add their attention output, so it's the previous layer with X. Okay, so the gradient can propagate across the network. Then we're going to apply the layer normalization too. So we're going to have X3, which is equals to layers dot layer normalization this spelling epsilon, yeah, okay, epsilon, like so. I think, yeah, there's it here. Okay, we apply this small value to avoid a division of 0. Then what we do, now we're gonna apply the multi-layer perceptron which we built. So it's gonna be x3 equals to, so did we pass in? Yeah, we passed it out. Okay, yeah, that's fine. I'm gonna say x3 equals to a multi-layer perceptron. We take x3 here, then we say hidden units equals to x dot shape. Then we say we multiply this by 2. We take the last shape. Yeah, the last shape. We multiply this by 2. Then we say x dot shape, which is -1. Then we apply the regularization rate, which is dropout rate, which is going to be 0.1. Okay, then when we're done, we apply the skip connection. So it's going to be x equals to layers dot add. What are we adding? We're adding the x3 and x2. Okay, and when we're done, we return x like so. Okay, if you don't understand this code here, please watch my transformer video. Essentially, you will understand the transformer architecture and how it is implemented. So when you see like us applying layer normalizations followed by multi-layer perceptron, you will understand actually, because this is like the attention transformer architecture, how it's being how it was structured. Okay, so just keep that in mind. Okay, let's look into another block that we're gonna build. So we can see that we have to build this MobileVIT block, right? And this MobileVIT block essentially is this whole entire thing here that we're looking at. So we can see they're calling it MobileVIT block. So we're gonna call this component here. Okay. What we're gonna do is that we're gonna say dev. We're gonna call this one MobileVIT. Then we're gonna call this block. Then we're gonna take x num blocks. Then we're gonna have a projection dimension. We're gonna have strides equals to 1. Okay. Then the local projections with convolution, we're gonna say local features is going to be equals to conv block. So we're calling the block that we created. Then we're gonna pass in x. Then the number of filters is gonna be equals to the projection dimension. Then strides equals to strides. Okay. We're gonna say local features equals to conv block, like so. Then we take the previous local features we say filters equals to projection dimension, and kernel dot size equals to 1. Then we have strides equals to strides. Okay, so let's remind ourselves, what does this mean? So we know that we had a convolution of n by n, and we projected this to a pointwise convolution of this 1 by 1 here. So these are the two components that we built. So this is what we call local representation layer. So we just build this thing here. Okay. Let me just remove this notification, and I'm just going to try to scroll down. Yep. So now we unfold into patches, then pass through the transformer. By that I mean we have to code this component here. Okay. So we're gonna say num of patches. We're gonna be equals to int. Then we say local features dot shape. Then we multiply this by local features. Okay, am I doing the right thing here? I doubt. So it's supposed to be local features. We take the second dimension, then we do a division by the patch size. Okay, patch size. Then we're going to have non-overlapping. These are non-overlapping, so it's non-overlapping patches. So non-overlapping patches is going to be equals to layers dot reshape. We're going to take the patch size, then we say nums of patches, then we take the projection dimension. Okay, then now we're gonna push these non-overlapping patches to our transformer block. Okay, so we're gonna say global features. So we then have this transformer block that we already built. We're using this block to take the non-overlapping patches. Then we say nums block. Okay, block 60. So it's gonna be num projection dimension. Okay, like so. So number of blocks. So I think yes, because I have a spelling error, like so. Yeah, then after we pass these non-overlapping patches into the transformer, then we have to fold them. So what we do is that we fold them into conv-like feature map. So we have these global features. So what we're gonna do is that we're gonna say folded feature map is gonna be equals to layers dot reshape, right? We taken local features. We take dimension from the first dimension all the way to the last dimension, and we take in the projection dimension. Okay, so then we pass in the yes, we're gonna pass in here the global features. Global features. Oops. Like so. I think after that we apply the pointwise, yes, the pointwise convolution. Then we get this. Then we have this fusion. So we're gonna concatenate this with the input. Okay. So we apply concatenator. So we're gonna say folded feature map equals to conv block. So this is conv block because we're gonna take folded feature map, whereby we say filters equals to x dot shape, right? Take the last dimension. Then we say kernel size, because of it's a pointwise, this is going to be 1. Then we're going to say strides, which is stride by default equals to 1, goes to that. So this is a pointwise. So what we need to do is that we need to take this and now we need to concatenate. So when we concatenate these, we're gonna have local and global features. So we call this local, global features. We're gonna say layers dot concatenate. We say x's across x's equals to 1. We have this skip connection, which we take x because they have the same dimension. So we're gonna take folded feature map here. Okay. Fuse the local and global using convolution. So for us to fuse these, yes, so we have concatenated them, but we fuse them using this convolutional layer. Okay, so we're gonna say local global features, okay, equals to conv block. Then we take in local global features. We apply filters equals to the projection dimension, then strides equals to strides. Okay, return local global features. I think we need to make sure that stride here is equals to 1 so that we can actually be able to concatenate. So if stride becomes 2, I think we might not be able to. Yeah, but essentially this is the MobileVIT. So we went through the paper, we explained this component in more detail. So now I'm just coding it up just to so that you have a clear understanding of how it's implemented from the code, right? So now you can see that we have these blocks. All of these blocks, we have them. It's just that now we need to bring them together, you know, in a sequential order so that we can get the logits. Okay, so that's what we're gonna look into. I didn't feel like coding the last part because of this last bit here. It's just like we're creating MobileVIT. So it's like we're pulling all the component that we already built. So all of these blocks here, we just like putting them together to build MobileVIT. So as you can see here, we have this we start with this convolutional block. Then we have these inverted residual block. Then we have another inverted residual block for this for downsampling. Then we have our first MobileVIT block. Firstly, we apply the inverted residual block. Then we have this MobileVIT block. Then we have the second MobileVIT block, which is here. So as you can see, essentially, it's like we're building these components. You see, it's like we have these components like so. So we just keep on bringing everything that we had. And the last step, as you can see, is a classification head, whereby we apply the global average pooling. Then we have a softmax here, so we're getting our logits, and we return the outputs, right? So that's what it is to this essentially. This is more like we're constructing the model, but the most important thing is these blocks here, because these are the building blocks. So if you have a good understanding of these blocks, then to understand how this is structured, it's going to be easy. So if you've read my paper, not my paper, my video, if you've watched it around the next VIT, whereby they state that sometimes constructing a model like this, what happened is that these first layers, right, because of these are convolutional layers, they get to be good at capturing locality, like local features, but they don't have the global features. And what they've realized is that putting these layers, the global transformers to capture the global features at the end, essentially this can be problematic. So what they did in the next VIT, I think it was next VIT, but yeah. So what they did was to introduce the global features at the beginning of the network. So firstly you have like your conv, but you still have your transformer there. So from the beginning of the network, these models tend to have the global picture of the input. So which was quite fascinating also to see. But one thing that I'll take is that you can see how the author, they structure this, right? Like, like they start with this convolutional block, they have this inverted block and stuff like that. So yeah, I'm not saying this is not important, but it's still important, because when you read different papers, you get to see where this transformer block is being placed. Like I said, that in the next VIT, this transformer block is placed with convolutional block at the beginning of the layers, and the intuition of the authors was that they've realized that these layers at the beginning, right, they don't get to have a global view of the input, so they tend to suffer. So because of now, they take these mobile block, they put it here, so the model, the layers at the beginning, they have a global view of the input image as well as local features, so that essentially build a more robust model. But yeah, I think anyway, that's how this was structured, and yeah, I think I really enjoy this. So in the next one, we're gonna see how we're gonna go through the self-attention. So yeah, the linear self-attention using PyTorch. So yeah, stay tuned, and yeah, we're gonna go through that. Thank you very much, guys. I'll see you in the next one.